So that's what, 66 2/3 miles per hour. So if we know we traveled at 200 miles in the 3 hours, then somewhere along the way we must have been going uh, 66 2/3 miles an hour, because that's the average speed over that time. Okay, that's the mean value theorem. Now, let's give a proof of the mean value theorem, and then we'll see how we can use it. So to prove the mean value theorem, we essentially turn it into Rolle's theorem. I actually think of it as saying, well, there's Rolle's theorem, because if you had it flat, then there'd be that point there, and then here's mean value theorem. So the mean value theorem is just Rolle's theorem with your head tipped. So let's consider the following function here, and what I'm trying to do is come up with the equation of that line, that red line that I drew, right, that goes through this point here at the end and that point there. So let's let g of x equal, let's just see, it's got to go through the point f of a, and then it has to have slope f of b minus f of a all over b minus a, and then times x minus a. So there's point slope form for the line. So that's that line right there. Some things to notice here. It's a linear function, so g of x is continuous on the interval from a to b. It's also differentiable, not f prime. How about g prime f? Sorry, g of x is differentiable on, well, the closed interval from a to b, so even more so the open interval. In fact, I can even say what g prime of x is. Why do I keep writing f? G prime of x is, right, this is just linear, so the derivative is going to be the coefficient in front of the x, and that's just f of b minus f of a over b minus a. Also notice, no, don't notice that. So now I'm going to define another function. Let h of x equal f of x minus g of x. Okay. So I'm going to look at h is going to be measuring the difference between the two, right? So f minus g for each value of x, f minus g. Okay. So now h of x is the one that I really want to look at here, because notice this here. Note that h of x is continuous. Why is it continuous? Because it's a difference between two continuous functions. H of x is differentiable. Why is it differentiable? Well, because it's the difference of two differentiable functions, and the derivative of a difference is the difference of the derivative, so yeah, the derivative of h will exist everywhere. Also, I want to point out that h of a equals 0, right? Because let's just double check this here, because this would be f of a minus g of a, but g of a, where's g defined? G defined is right here. When I plug an a in for x, this is the only place the x appears, is right there. So that becomes a 0 times that is 0 plus f of a. That's just equal to f of a. So this is f of a minus f of a, which is of course 0. Okay, so h of a is equal to 0. I also want to claim that h of b is equal to 0, right? And I can see that because h of b is equal to f of b minus g of b, which is f of b minus, and when I plug a b into this g, let's see, plug a b in, this would be a b minus a, and then it divides by the b minus a, so those two would cancel out. Then you got an f of a plus f of b minus f of a, and the f of a's will cancel out, and you're just left with f of b. So it's f of b minus f of b, which is 0. So h actually satisfies the conditions of Rolle's theorem, because it's continuous, it's differentiable, and it is, and the endpoints have the same function values. So by Rolle's theorem, there exists a C on the open interval somewhere between A and B, so that f prime of c equals 0. Not f prime, h prime. Right? H is the one that's satisfying Rolle's theorem, so that's saying that h prime of c is equal to 0. Well, what is h prime of c? Right? So 0 equals h prime of c equals, well, h prime of c is f prime of c minus g prime of c. But g prime of anything, g is a straight line, right? G was this red line, and the slope is the same everywhere. It's f of b minus f of a over b minus a. So I've got 0 equals f prime of c minus f of b minus f of a over b minus a, and then I get the result that I wanted, that f prime of c equals f of b minus f of a over b minus a. So somewhere in the middle, there's got to be a spot where the derivative of the function is equal to the average slope of the function across that interval. Okay. One thing to point out here is that the mean value theorem is an existence theorem. It says there exists a point C on the interval where the slope of the tangent line is equal to the average slope. It is, however, but it doesn't say where C is. It's somewhere in the middle. It doesn't tell you where. It just says, hey, there is one. Okay, so it's not a constructive proof. It doesn't find the point C. It just says, yeah, it's there somewhere. It's got to be there. Okay. One last thing I want to say about the mean value theorem before we move on to doing some examples with it and seeing the consequences of the mean value theorem is that sometimes the mean value theorem is written this way, and sometimes they write it this way, where they say b minus a times f prime of c equals f of b minus f of a. We'll see later on where that might be useful. That is, later on as in Calc 2, where being able to do something like this is particularly nice. We'll be looking at, this might look like an area of a rectangle. B minus a is the distance across the bottom, and this might be a height function or something like that. So there's times when you'll see it this way, but for the most part, in Calc 1, it'll look like that, the consequence of the mean value theorem. All right, so now we're going to, in the next video, take a look at some examples that are generally given as homework problems of how do you actually find C. This doesn't, mean values theorem doesn't tell you where it is, but how would you find it? So that's next. Now let's take a look at the mean value theorem. The mean value theorem looks a lot like Rolle's theorem, except one little difference. It says if f of x is a continuous function on the closed interval from a to b, and f of x is differentiable on at least the open interval from a to b, then there exists a c on the interval a to b such that f prime of c equals, and let's see if we can figure out what needs to be there. Looking at a picture, here's a, here's b, here's f of a. Now, here's the difference between the mean value theorem and Rolle's theorem, is that in Rolle's theorem, f of a equaled f of b. Well, in the mean value theorem, I don't need that, so f of b might be different. And I'm drawing f of b bigger than f of a, but it doesn't have to be. This might be the other way around. They're just potentially different. Okay. So the thing is, I can't necessarily guarantee a slope of 0, but I can guarantee some other slope, right? That is, if it's continuous, it means I can draw without picking up my pencil. If it's differentiable, there's no sharp corners, right? So maybe it looks something like that. Or, maybe it does a whole bunch of goofy things, but it doesn't take any sharp corners, and it doesn't ever have any discontinuities. So it's not necessarily a derivative 0 somewhere, but there is necessarily the derivative of what it would be if it were just a straight line, right? If you just drew a straight line between here and there, then that would always have the same slope. So that's pretty much the only thing I can guarantee is that slope. And in fact, yeah, right up here, there should be a place where the tangent line to the curve is parallel to that one right there. So this would be the point C right here. And the slope that we're guaranteeing is the slope of that straight line between them. So that would be rise over run here, right? So f of b minus f of a over b minus a. And that's the mean value theorem. Notice that the word, to me, the word mean in the sense of mathematics is generally used as an average. You take the mean of a bunch of numbers, that's the same as the average of a bunch of numbers. And so what we're finding here is essentially the average slope. If we think of this as in terms of a position function and the input is time, then we might say, you know, at time 2 we were at milepost 100, and at time 5 we were at milepost 300. So what did I say? I said time 2 to time 5 and 100 to 300. So in those 3 hours we traveled 200 miles. So 200 miles divided by 3, 200 miles divided by 3, that would be, I don't know, whatever 200 divided by 3 is. Why can't I do that? 60 something, right? So